Welcome to the Deep Dive, where we slice through the noise and get you straight to the heart of what truly matters. Today, we're plunging into a topic that, well, it feels like it just burst onto the scene, right? Artificial intelligence. It seems like it's reshaping industries almost overnight.
It really does. It's dominating headlines, sparking both huge excitement and, frankly, quite a bit of concern. It seems to be absolutely everywhere you look.
Exactly. But here's the surprising thing, the thing we really want to unpack today. AI's story.
Yeah.
It isn't actually that new at all. Its history is, well, it's far richer, much more complex, and you could definitely say profoundly cyclical.
That's such a crucial distinction, and it's one that often gets missed, I think, amidst all the current buzz. When you actually trace the path of AI, you pretty quickly realize it's not just this straight line of relentless upward progress. Not at all. Instead, it's been this really fascinating journey. It's marked by these exhilarating periods of intense innovation and just boundless optimism, what people often call AI summers. But then these are followed by pretty stark AI winters, periods of disillusionment, skepticism, and importantly, dramatically reduced funding.
Right. Summers and winters.
Yeah. So our mission today is to take the source material you've provided and really trace this captivating kind of up and down history. We want to pull out the key turning points, the really big ideas, and some genuinely surprising facts, stuff that will make you truly well-informed on where AI actually comes from, and maybe even more importantly, where it might be headed next.
So yeah, buckle up. This deep dive, it's designed to give you a much clearer understanding of the deep forces driving AI's evolution.
Yeah.
We want to explain why certain big promises came and went, why they didn't quite pan out initially, and also show how today's really breathtaking breakthroughs, they aren't magic. They're actually built on decades of foundational work, often work that doesn't get talked about much.
It's a story of resilience, really. Reinvention, human ingenuity. It'll definitely change the way you think about intelligent machines, I believe.
Okay, so where do we start this journey? Not with silicon, you're saying?
No, not really. To truly unpack this, we have to go back further. We need to start, surprisingly perhaps, with philosophy and a man named Alan Turing. Long before computers as we know them even existed, the whole idea of machines thinking was, well, it was pure speculation, mostly science fiction.
Right.
But it was Turing, with his absolutely seminal 1950 paper, Computing Machinery and Intelligence, who laid the intellectual groundwork for modern AI.
Okay, 1950. So what was it about that paper? What was his pivotal contribution that let people actually start working on this really philosophical question? Can machines think? How did it become something engineers could, grapple with?
That's where Turing's genius really comes through. He understood, I think, that getting bogged down in defining thinking itself, that would just be a philosophical dead end, a quagmire.
Makes sense.
So he brilliantly sidestepped the whole issue. He proposed instead a pragmatic, measurable goal. He called it the imitation game.
Which we now all know as the Turing test. Such an elegant solution, wasn't it? Almost mischievous, tackling this huge abstract problem in such a practical way.
It really was a stroke of brilliance. And the test itself, it seems deceptively simple when you describe it, but its implications are just profound. Imagine you're a human interrogator, you're communicating only via text, no visual cues, no hearing a voice with two hidden entities.
Okay.
One's another human, the other's a machine. Your only job, figure out which is which.
Right. Can the machine fool you?
Exactly. If the machine can consistently fool you, the human judge, into believing it's human, then, well, according to Turing, for all practical purposes, it has exhibited intelligent behavior. This ingenious framework gave a concrete, maybe controversial, but definitely concrete objective for this new field of AI research.
It took it out of the philosophy department and put it into the lab, essentially.
Precisely. It gave engineers and scientists a tangible benchmark, something to actually aim for, rather than just an abstract concept to debate endlessly. It shifted the focus to practical engineering.
And it didn't take long after Turing's idea started circulating for AI to get its kind of official birth certificate, right?
No, not long at all. We're talking at the summer of 1956. Specifically, the Dartmouth Workshop.
Ah, yes, Dartmouth. That sounds like more than just a conference. It feels foundational, almost legendary now.
It absolutely was. The Dartmouth Workshop was pulled together by this visionary group of pioneers, John McCarthy, Marvin Minsky, Nathaniel Rochester, and the great Claude Shannon. They handpicked a small but absolutely brilliant group of researchers, invited them to spend a whole summer just wrestling with this idea of artificial intelligence.
Wow, a whole summer.
Yeah. And their proposal, the declaration that basically launched the entire field, was, well, for 1956, it was just extraordinary. They proposed that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it.
That's incredibly bold for 1956, given the computers they had back then.
It speaks volumes about their unbridled optimism, doesn't it? The sheer confidence.
You can almost feel it radiating off that statement. This feeling that major breakthroughs, maybe even true machine intelligence, were just around the corner, like maybe just a few years away.
Oh, absolutely. There was this incredible confidence, this almost infectious belief that if they could just precisely describe what intelligence is, they could definitely build it. It was like a gold rush, but for the mind.
So this early optimism, fueled by Dartmouth, it quickly led to actual programs being built.
Swiftly. It translated directly into developing some truly pioneering programs. Now, okay, by today's standards, they seem rudimentary, obviously, but at the time, they were revolutionary. They offered these tantalizing glimpses of AI's potential. Take the Logic Theorist program, developed by Alan Newell and Herbert Simon back in 1955, even before Dartmouth.
Logic Theorist, what did it do?
It was capable of proving mathematical theorems, theorems from Whitehead and Russell's Principia Mathematica, a task previously thought to require real human insight, logic, deduction.
So proving theorems, how big a deal was that really? What did it show about machine potential for, like, human reasoning?
It was profoundly significant because the logic theorist, in a way, it mimicked the deductive process of a mathematician. It demonstrated that a machine could actually engage in symbolic reasoning, problem solving.
It wasn't just crunching numbers.
Exactly. It explored different paths to find a solution, much like a human trying to solve a puzzle. It was this powerful proof of concept. It showed computers could go beyond just arithmetic and start tackling problems needing abstract thought. It really ignited the belief that, yeah, maybe we can formalize human thought processes into algorithms. It seemed possible, maybe even within reach.
Okay, so that's logic. But then there was also language, right? ELIZA.
Yes, ELIZA came a bit later, 1966, developed by Joseph Weissenbaum. It was one of the very first programs designed to engage in, well, what looked like natural language conversation.
How did it work? Was it actually understanding?
Not really understanding, no. Its mechanism was quite clever, but deceptively simple for the time. It mostly used pattern matching and substitution rules. It would often just rephrase the user's input as a question. Weissenbaum famously modeled it on a Rogerian psychotherapist.
The therapist persona.
Right. So it would mostly reflect statements back. If you typed, "I am sad," it might respond, "Why do you say you are sad?" Simple tricks, but surprisingly effective.
And the effect it had was huge, wasn't it? Even though it had, as you say, this incredibly superficial understanding, it wasn't getting it.
Not at all. But the effect on users was profound and, honestly, unexpected. People would get deeply engaged in conversations with ELIZA. Sometimes they'd apparently forget they were talking to a machine.
There are famous stories, right? People sharing really personal feelings.
Exactly. Anecdotes of people confiding deep secrets, or Weisenbaum's own secretary reportedly asking him to leave the room so she could talk privately with the program. It really highlighted something fundamental about human psychology, I think. Our tendency to project intelligence, personality, even empathy onto systems, even really simple ones.
It showed our perception of AI could easily outpace the actual technology.
Absolutely. It sparked the imagination about what computers could do, even if the tech itself wasn't nearly as smart as it seemed. But, as we know, that early optimism, it didn't last forever.
No, it didn't. And that brings us almost inevitably, doesn't it, to the first AI winter, that chill that started to creep in.
Yeah. After those heady days of grand pronouncements and just boundless ambition in the 50s and 60s, that initial excitement began to curdle into, well, widespread disillusionment. The really audacious promises, especially of general human-level intelligence, they remained stubbornly out of reach. And that led to a stark, sobering reality check for the whole field.
Which meant
funding started drying up. Interest from governments, private companies, it just declined dramatically. The well started to run dry.
And nothing really crystallized that growing disillusionment, quite like the Lighthill Report in 1973.
Ah, yes. The Lighthill Report.
This wasn't just some academic paper. This was a big deal, commissioned by the British government to evaluate AI research. And the conclusions from Sir James Lighthill, they were harsh.
Scathing is the word often used. He essentially declared that AI research had profoundly failed to deliver on its big promises, that it hadn't produced a major impact on any significant real-world problem. Ouch indeed.
What was his main argument? Why did he think it had failed so badly?
His core argument was pretty sharp. He said AI methods, while maybe impressive in very limited contexts, were only effective on what he rather dismissively called toy problems.
Toy problems.
Yeah, simplified constrained scenarios, proving theorems in a closed logical system, navigating a tiny world made of blocks. Stuff AI programs could actually manage back then.
No, they couldn't scale up.
Exactly. When researchers tried to apply those same methods to real-world complexity, they just fell apart. They got hopelessly bogged down. And Lighthill pinpointed the reason, something he called combinatorial explosion.
Okay, combinatorial explosion. That sounds important, but also a bit technical. Can you break that down? What does it really mean?
Sure. Think about a game like chess. Seems straightforward, right? But for a computer to play well, it needs to think ahead. It has to consider all its possible moves from the current position.
Okay.
Then, for each of those moves, it has to consider all the opponent's possible counter moves, and then its own next moves, and so on. It builds out this branching search tree of possibilities.
Right, it gets big fast.
Exponentially fast. That's the explosion. Lighthill pointed out that the number of possible game states, the number of branches in that tree, grows incredibly quickly with each step, each move ahead you look. In chess, after just a few moves, the number of potential board positions becomes astronomical. It just dwarfs anything manageable.
So the computers just couldn't handle it.
Not back then, no. They simply lacked the processing power, the memory to explore that search tree deeply enough. They couldn't look far enough ahead to be truly effective against a skilled human in a complex game like chess.
They were stuck with shallow searches.
Right, making them easily outplayed. This wasn't just a small technical hurdle, it was a fundamental miscalculation of the complexity involved. It forced a major rethink about how you might build intelligence. Maybe not through exhaustive search, but something else.
Heuristics, pattern recognition, seeds for later perhaps.
Exactly. But at the time, it was a huge blow. It suggested the whole approach might be flawed, or at least the hardware was nowhere near ready.
And the Lighthill report, it had real-world consequences, didn't it? It wasn't just academic criticism.
Oh, absolutely devastating consequences. The report directly led to severe, widespread funding cuts for AI research, especially in the UK, which had been a major center.
Didn't have spread.
It had a global ripple effect, yeah. Other governments, private investors, they saw the report and became much more skeptical, much more reluctant to pour money into what now looked like maybe an academic pipe dream.
So AI went underground again.
Pretty much. Research didn't stop entirely, of course, but it definitely became less visible, less hyped. Researchers often continued their work, but maybe under different labels.
Like computer science or...
Computational linguistics, pattern recognition, yeah. The focus shifted, became more humble, more geared towards specialized practical applications rather than chasing that grand goal of general AI. It was a time for quiet work, perseverance, maybe going back to basics.
So another period where AI kind of retreated. Seemed like it might just fade away. But the cycle continues, right? Things changed again in the 1980s.
They did. The 80s brought this unexpected, almost dramatic resurgence, a kind of temporary thaw in the AI winter. And this was driven largely by the surprising commercial success of something called expert systems.
Ah, expert systems,
Yeah.
right. This felt like AI was suddenly practical, useful again.
Precisely. Expert systems represented a much more pragmatic approach. Instead of trying to build general intelligence, these programs aimed to replicate the decision-making of a human expert, but only within a very specific, narrow field.
How did they work? What was under the hood?
They typically operated based on a large knowledge base. This contained lots of facts relevant to the domain, plus a set of if-then rules. These rules were usually painstakingly extracted from actual human experts through long interviews. Knowledge engineers, they called them.
So bottling up an expert's knowledge.
That's a good way to put it, like bottling the specialized knowledge of, say, a master geologist identifying mineral deposits, or a seasoned doctor diagnosing specific diseases, or an engineer configuring complex equipment.
And they actually worked, delivered real value, because that was key after the first winter.
They really did deliver tangible results, which was huge. The classic, almost legendary example is XCON, developed for Digital Equipment Corporation, DEC.
DEC, right.
Yeah.
Big computer company back then. What did XCON do for them?
XCON was designed to automatically configure DEC's complex VAX computer systems. When a customer ordered a VAX, it involved choosing from thousands of possible components, different processors, memory types, disk drives, peripherals.
A complicated puzzle.
Extremely. Getting the configuration right, ensuring everything was compatible and correctly connected, was a massive headache. Mistakes were costly. XCon took over that configuration task. It used its rule to ensure all the selected components worked together, that the final system made sense.
And the impact.
Huge. There are stories, maybe slightly apocryphal but directionally correct, that DEC literally had warehouses full of misconfigured computers before XCon. Returns, reworks, it cost them millions. XCon virtually eliminated those errors, streamlined the whole process. Saved DEC enormous amounts of money year after year. Its success was undeniable proof that AI, even in this narrow rule-based form, could provide immense commercial value.
And that success, naturally, sparked another wave of investment. AI was back in fashion.
Absolutely. Suddenly, AI was hot again. Venture capital flowed in. This led to the rise of specialized hardware companies, particularly those building machines optimized for the Lisp programming language.
Lisp machines. Why Lisp?
Lisp was the dominant language in the AI research community at the time. It was very flexible for symbolic manipulation, which was key for rule-based systems. So companies like Symbolics, Lisp Machines, Inc., they popped up, selling expensive hardware tailored for AI development.
But this AI spring, this expert system, boom, it didn't last either, did it? We headed into the second AI winter in the late 80s. What went wrong this time?
Well, the inherent weaknesses of expert systems, the things maybe overlooked during that commercial honeymoon phase, they became glaringly apparent. And that led directly to their downfall.
What weaknesses? They sounded so successful with XCon.
They were successful in narrow contexts, but they had major drawbacks. First, they were incredibly expensive to build. It took years of effort from highly paid domain experts and those knowledge engineers to extract and codify all the rules. And, crucially, they were even more expensive and complex to maintain. Every time a rule changed, a new product came out, a new regulation appeared. Someone had to manually update the knowledge base and rules. It was painstaking.
And they were also brittle. I remember reading that.
Yeah. Yes, brittleness. That's a key concept. It refers to their fundamental inability to handle situations even slightly outside their meticulously programmed rules.
So no flexibility.
None. If you gave an expert system a problem that deviated even a little bit from what it was explicitly taught, it would often just fail spectacularly, give nonsensical answers, or just freeze up. They lacked common sense, any real understanding, any ability to adapt or generalize. Imagine that medical expert system, great for textbook cases, but stumped by an unusual symptom a human doctor might intuitively figure out.
Okay, I see. That brittleness plus the cost.
Right. That fundamental lack of flexibility, combined with the huge upfront cost and the even bigger ongoing maintenance costs, meant that for many companies, the return on investment just wasn't there in the long run. Disillusionment set in again.
And then the hardware market collapsed too. The Lisp machines.
That was the other shoe dropping. The specialized Lisp machine market, which had thrived alongside expert systems, it just imploded. Because general-purpose computers, workstations from companies like Sun Microsystems, and then powerful PCs from Apple and IBM, they became incredibly powerful and, most importantly, far, far cheaper. These new machines could run Lisp perfectly well, alongside everything else. So why buy an expensive, single-purpose Lisp machine anymore? The specialized hardware became obsolete almost overnight.
So a double whammy. The software approach, expert systems, hit its limits, and the specialized hardware became uneconomical.
Exactly. That confluence of factors ushered in the second AI winter. Renewed funding cuts, AI companies going bankrupt or pivoting, talent leaving the field. Skepticism was rampant once again. AI was back in the wilderness.
Another winter. But again, the cycle turns. Even in the wilderness, something new was brewing. The late 90s, early 2000s. This seems like a really pivotal turning point, a shift away from rules entirely.
A massive shift, a subtle but really profound revolution away from that rule-based, explicitly programmed AI of expert systems towards something fundamentally different, statistical machine learning.
Machine learning. Okay.
Yeah. This was driven by a growing realization, I think, that trying to manually write down all the rules for intelligence or even expert knowledge was probably just intractable. too complex, maybe impossible. So researchers started focusing more on algorithms that could learn patterns directly from data without being explicitly told every single rule.
Learning from examples, basically.
Essentially, yes. And this fundamental revolution, it wasn't just one single breakthrough idea. It was really made possible by the powerful convergence of three key developments that happened almost in perfect sync.
Okay, what were those three? They sound critical for where we are now.
The first, and you could argue the most important, was the explosion of vast data, what we now call big data. With the rise of the internet, the digitization of everything, web pages, emails, transaction records, scientific data, early social media, suddenly we were generating absolutely colossal amounts of digital information, unprecedented amounts.
Right, data was everywhere.
And this data became the essential fuel for machine learning algorithms. Without these massive data sets, the algorithms simply couldn't learn effectively. They'd be like an engine without gasoline.
Okay, so data is fuel. What's the engine?
That's the second crucial development, a dramatic and continuous increase in computational power. Moore's law was still going strong, processors were getting faster and faster, but just as importantly, powerful CPUs became much more affordable. What used to require a supercomputer could now sit on your desktop, or at least be accessed relatively cheaply in server farms.
So we could actually process all that data.
Exactly. It became feasible, technically and economically, to train much more complex machine learning models on these huge new data sets. Algorithms that maybe existed theoretically for years but were just too computationally expensive to run could now actually be implemented and tested.
Makes sense. Data power. That was the third piece.
The third was the fundamental shift to statistical models themselves. The algorithms changed. Instead of relying on humans writing if-then rules, the very thing that made expert systems brittle researchers developed algorithms that could learn to identify patterns, correlations, and make predictions directly from the raw data.
So the intelligence wasn't programmed in, it was learned.
Precisely. It was a profound move from programmed intelligence to learned intelligence. These algorithms could sift through terabytes of data, find subtle statistical relationships humans might miss, and then apply those learned patterns to new unseen data. It was a fundamental reimagining of how machines could behave intelligently, moving from deterministic rules to probabilistic, data-driven learning.
And this new approach got a huge public validation moment, didn't it? Even if the system itself wasn't strictly learning in the modern sense. I'm thinking of Deep Blue.
Deep Blue versus Kasparov, 1997. Yes, an absolutely iconic moment. Everyone remembers where they were when Kasparov lost.
Well, maybe not everyone, but it was big news.
Fair enough. But it captured the world's imagination. Now, what's fascinating is the nuance there. Deep Blue was a phenomenal feat of engineering, no doubt, but it was primarily a brute force system, an incredibly sophisticated one, mind you. It used custom-built hardware, highly optimized algorithms. It could calculate and evaluate something like 200 million chess positions per second.
Wow. Just raw power.
Essentially, yes. It tackled that combinatorial explosion Lighthill talked about, not through clever learning, but through sheer overwhelming computational power. It explored that massive search tree. So Deep Blue didn't really learn like modern ML models do. It was executing pre-programmed calculations at superhuman speed.
But the symbolism.
The symbolism was immense, beating the human world chess champion at his own game. It was this powerful public demonstration of what computation could achieve. It signaled that a new era was dawning, one potentially driven by massive compute and data. It proved that complex intellectual problems, previously the sole domain of humans, were now potentially conquerable by machines.
And while Deep Blue was grabbing headlines, something else was quietly stirring in the background, right? Something that would become even more important later.
Yes. During this same period, the late 90s, early 2000s, this once dormant idea started to reemerge from the shadows. Neural networks.
Neural nets, inspired by the brain.
Loosely inspired, yes. These are computational models with interconnected nodes, or neurons, that process information. They'd actually been around since the 40s and 50s, people like McCulloch and Pitts, Rosenblatt, but they'd largely fallen out of favor after the first AI winter. There were theoretical limitations identified, particularly around training networks with multiple layers, and frankly, the computational power just wasn't there to make them practical.
But now, with more data and more power.
Exactly. The promise of neural networks started to seem achievable again. Researchers like Geoffrey Hinton, Jan LeCun, Yoshua Bengio, names you hear all the time. Now they began making quiet but crucial breakthroughs in figuring out how to effectively train these deeper networks. They were laying the groundwork for the next massive leap.
And what a leap it turned out to be. The 2010s. This really feels like the start of the modern AI era, what people started calling another AI summer. And the driving force was deep learning.
Absolutely. The 2010s ushered in this period of truly accelerated progress, an unprecedented AI summer, powered almost entirely by the explosion of deep learning.
Okay, so deep learning. It's a type of machine learning, but what makes it deep?
It specifically refers to using artificial neural networks that have multiple layers, often many, many layers stacked on top of each other, hence deep.
And why are multiple layers important?
This multi-layered structure, this depth, allows the network to learn increasingly abstract and complex features or representations of the data automatically in a hierarchical way. Think about image recognition. The first layer might learn to detect simple things like edges or corners. The next layer might combine those edges to recognize simple shapes. Subsequent layers might combine shapes to recognize more complex objects like eyes or noses, and eventually whole faces or entire scenes.
Ah, okay, so it builds up complexity layer by layer.
Exactly. And the real breakthrough was its ability to automatically extract these useful, complex, hierarchical features directly from the raw data, like pixels in an image or sound waves in audio. This bypassed the incredibly laborious process of feature engineering that dominated earlier machine learning.
Future engineering.
That's where human experts had to manually figure out and tell the algorithm exactly what features in the data it should pay attention to. Like for face detection, maybe look for two dark circles above a horizontal line. It was slow, difficult, and often the bottleneck.
So deep learning learns the important features itself, just from the data.
Precisely. That self-learning of features was revolutionary. But this amazing capability required truly immense amounts of computation, which brings us to a critical enabler, GPU computing.
GPUs, graphics processing units. From video games, right? How did gaming hardware become the key to AI?
It's a fascinating example of technological crossover. GPUs were originally designed to render complex 3D graphics in games, which involves performing millions, even billions, of relatively simple mathematical calculations simultaneously in parallel.
Lots of simple things at once.
Exactly. And it turned out that the core computations needed to train deep neural networks, primarily matrix multiplications, are very similar. They also involve tons of parallel simple calculations.
So GPUs were perfectly suited for it.
Perfectly suited. While CPUs are great for complex sequential tasks, GPUs excel at this kind of massive parallel number crunching. When researchers realized this and started adapting GPUs for training neural nets, it was a complete game changer.
How much faster?
Dramatically faster. Training times plummeted. What might have taken weeks or months on CPUs could suddenly be done in hours or days on GPUs. This massive speed-up made it practical to experiment with much larger data sets and much deeper, more complex network architectures. It was absolutely critical for making deep learning feasible and driving the rapid progress we saw. It democratized deep learning research.
So faster training, bigger data. That progress needed a showcase moment. And it got one in 2012, didn't it? The ImageNet challenge.
Oh, absolutely. ImageNet 2012 was the watershed moment, the moment deep learning truly announced its arrival on the world stage.
What was the challenge?
ImageNet is this massive data set of millions of labeled images across 1,000 different categories, types of dogs, cars, household objects, you name it. The challenge was to build a system that could classify these images accurately. In 2012, a deep convolutional neural network called AlexNet, developed by Alex Krzyzewski, Ilya Sutskever, and Jeff Hinton, just blew the competition away.
By how much?
It won by a huge margin. Its error rate was significantly lower than any of the previous winners, which had all used more traditional computer vision techniques. It wasn't just a win, it was a domination.
And the impact?
It stunned the computer vision community. It was undeniable proof of deep learning's power, particularly for image tasks. It ignited this massive wave of interest, investment, and talent shifting towards deep learning across the entire tech industry. Everyone wanted in. It proved deep learning wasn't just academic theory. It was a practical technology with immense potential.
Okay, so ImageNet conquered vision. But language? Language is different, harder maybe. What was the breakthrough there that led to things like ChatGPT?
You're pointing towards another absolutely seminal moment, this time in 2017, the publication of a paper titled "Attention is All You Need."
Catchy title.
Isn't it? And it introduced the transformer architecture. This was a complete game changer for natural language processing, NLP, a real paradigm shift.
How so? What was wrong with previous approaches?
Before transformers, the dominant models for language were things like recurrent neural networks, RNNs, or slightly more advanced versions called LSTMs, long short-term memory networks. These models process language sequentially, word by word, kind of like how we read, which seems intuitive, but it makes it really difficult for them to capture long-range dependencies in text.
Long-range dependencies, like...
Like how a word at the beginning of a long paragraph might relate to or depend on a word several sentences later, or understanding pronoun references across long distances. RNNs struggled with that because information tended to fade as they processed sequentially. It was a major bottleneck for understanding complex text.
Okay, so how did the transformer architecture fix that? What's the attention part?
The brilliance is the attention mechanism. Instead of processing word by word, the attention mechanism allows the model to dynamically weigh the importance of all words in the input sequence relative to each other simultaneously, regardless of how far apart they are.
So it can look at the whole sentence or paragraph at once.
Essentially, yes. When processing a particular word, say a pronoun like it, the attention mechanism allows the model to instantly attend to all other words in the input and figure out which noun it most likely refers to, even if that noun appeared much earlier. It learns which words are most relevant to understanding the current word's context.
And that's faster.
Critically, yes. Because it doesn't have to process sequentially, it can perform many of these attention calculations in parallel. This massively speeds up both training and inference compared to RNNs. This combination, the ability to effectively model long-range dependencies and process data in parallel, was a monumental improvement. The transformer architecture quickly became the foundation for essentially all modern large language models. It unlocked the path to the current AI explosion.
And explosion really feels like the right word for this current decade, doesn't it? We are absolutely living in the era of large language models and LLMs and generative AI. It's inescapable.
It's an unprecedented AI summer, no question. LLMs, as you said, are these massive neural networks built directly on that transformer architecture we just talked about. But their defining feature isn't just the architecture, it's the sheer scale. They are pre-trained on truly mind-boggling amounts of data.
How much data are we talking?
Sometimes trillions of words, terabytes upon terabytes of text and code scraped from the internet, digitized books, all sorts of digital sources. This massive, unsupervised pre-training allows them to learn incredibly complex patterns, grammar, facts, reasoning abilities, even nuances within human language, to a degree we've never seen before.
And it's not just the scale, it's what they can do with that learned knowledge, right? That's the magic part.
Exactly. Their defining characteristic is their remarkable versatility, what people often call emergent capabilities. They can perform this vast range of tasks.
Like writing code.
Writing sophisticated code, composing professional emails, drafting marketing copy, generating creative stories or poems, summarizing long, dense documents, translating languages. The list goes on and on.
And the key is, they weren't specifically programmed for each of those tasks.
Precisely.
Yeah.
That's the mind-blowing part. This generalization comes from the massive pre-training. You don't explicitly program an LLM on how to write a Python function to sort a list or compose a sonnet about autumn. You simply prompt it, give it instructions in natural language, and it leverages the patterns and knowledge it learned during pre-training to generate a relevant, coherent, and often surprisingly high-quality response. It's a totally different paradigm from older AI.
We got the first big public glimpse of this power with OpenAI's GPT-3 back in 2020. That made waves, especially in the tech world.
It did. GPT-3 showed a stunning leap in language generation and understanding.
But it was really ChatGPT, released late in 2022, that took this tech mainstream, right? Put it in the hands of millions.
Absolutely. ChatGPT's public release made AI a household term again almost overnight. It sparked this incredible wave of public excitement, curiosity, and, yes, debate on a scale we probably haven't seen since those very early optimistic days of Dartmouth, maybe even bigger.
And the pace hasn't slowed down. If anything, it's accelerating. Competitors are pushing things even further.
For sure. Companies like Google, with their Gemini models and others, are pushing hard into multimodality.
Multimodality. Meaning?
Meaning these newer models aren't limited to just text. They can understand, reason across, and generate content from multiple types of data simultaneously: text, images, audio, even video.
So you could show it a picture and ask questions about it.
Yes, or more complex things. You could show a model like Gemini, say a diagram from a physics textbook and the accompanying text explanation, and it could potentially understand the relationship between them, answer complex questions about the concepts, or generate a new explanation integrating both modalities. It's about moving towards AI that can perceive and reason about the world in a more holistic way, more like humans do, using multiple senses. It really extends AI's capabilities far beyond just text.
This whole AI boom, It's undeniably exciting.
Yeah.
Creating new tools, new applications, disrupting industries, maybe even creating entirely new ones at this incredible speed. But it's also, quite understandably, bringing a whole host of really complex societal questions and challenges right to the forefront. Things we can't ignore.
Absolutely. The very power of these models creates significant challenges. Take generative AI, the ease with which it can create incredibly realistic text, images, audio, video. It brings serious concerns about misinformation.
Deepfakes. Fake news on steroids.
Potentially, yeah. Discerning what's real online becomes much harder when convincing fakes can be generated so easily and cheaply. That's a huge challenge for trust and democracy. Then there are the impacts on things like academic integrity. How do educators assess student learning when sophisticated essays or code solutions can be generated instantly?
Yeah, that's a tough one.
And a really crucial area is ethics, particularly around bias. These models learn from vast amounts of human-generated data from the internet and books. And if that data reflects historical societal biases, racial, gender, cultural biases, the AI can inadvertently learn and perpetuate, even amplify those biases.
So it could lead to unfair outcomes.
Potentially, yes. In areas like loan applications, hiring decisions, even criminal justice risk assessments. If the AI is biased, its decisions could reinforce existing inequalities. Ensuring fairness and mitigating bias is a massive area of ongoing research and debate. Responsible development is paramount.
And beyond bias, there are these huge discussions about the future of work, right? Will AI take jobs, create new ones?
That's the multi-trillion-dollar question, isn't it? How will AI automate tasks, change required skills, and ultimately affect employment levels? Will it lead to widespread job displacement or create new kinds of jobs we can't even imagine yet? Economists are intensely debating this.
And then there's the legal and regulatory side. Who owns AI-generated content, especially if it learned from copyrighted material?
Exactly. Huge questions around intellectual property. How do we govern these powerful systems? Ensure accountability when things go wrong? What regulations are needed to guide development and deployment safely and ethically?
These aren't easy questions with simple answers.
Not at all. They're being actively debated by policymakers, legal experts, ethicists, and industry leaders worldwide right now. It's a really complex, fast-moving landscape.
It really highlights that every AI advancement, every summer, brings not just cool new tech, but also this profound responsibility to think about the societal consequences.
Couldn't agree more.
So, as we kind of wrap up and reflect on this whole incredible journey, it seems abundantly clear that the central theme holds. AI's evolution hasn't been smooth. It's been this dramatic, sometimes bumpy ride defined by those cycles. Hype, disappointment, hype again.
Summers and winters, yeah. But the crucial insight, I think, the most important takeaway, perhaps, is that each cycle, even those difficult winters with less funding and more skepticism, wasn't actually a dead end.
Right. They served a purpose.
They absolutely did. They pushed the field in new directions, often forced it to become more pragmatic, more rigorous. Those winters weren't times of complete stagnation. They were often periods of necessary reflection. Researchers had to confront the limitations of their current methods, focus on more fundamental problems, develop better mathematical tools, better statistical approaches.
So today's LLMs and generative AI, they didn't just appear out of nowhere.
Not at all. They are the direct result, the culmination of decades of that foundational research, much of it done quietly during those lean winter years. Combined, of course, with those critical hardware advances like GPUs and the sheer availability of massive data that only the internet age could provide, it's a real testament to scientific persistence, building layer upon layer.
So, yeah, the path to intelligent machines, it's not that straight line. It's more like a winding road with detours, a series of adaptations, pivots, big paradigm shifts.
That's a great analogy, like a scientific ecosystem that learns, adapts, builds on past failures just as much as successes. It's constantly refining its approach to tackle bigger and bigger challenges.
So looking ahead now, what's next on that road? What can we anticipate?
Well, we can certainly expect a continued push towards more capable and probably more efficient models. There's a big drive to make these massive models smaller, faster, cheaper to run, maybe even runnable on local devices like phones or laptops. And that push into multimodality we talked about will definitely accelerate. AI systems that can seamlessly integrate and reason with information from text, images, audio, video, becoming much more versatile and contextually aware, moving beyond just generation to real understanding across senses.
And alongside the tech development, the focus on ethics and societal impact will only grow, presumably.
It has to. As the capabilities expand, the urgency to address those complex ethical challenges, the questions of bias, fairness, safety, control, that becomes even more critical. There'll be an increasing global emphasis, I believe, on responsible AI development,
Wow.
on ensuring these powerful systems align with human values, and that their benefits are shared broadly, rather than just creating new problems or widening existing gaps.
And the ultimate goal, that dream of artificial general intelligence, AGI, human-level AI.
That remains the grand challenge. AGI, an AI that can learn, understand, and apply knowledge across the full range of human cognitive tasks with common sense and consciousness, that still seems like a very distant goal. Incredibly complex, maybe even fundamentally different from the path we're currently on. But even short of AGI, the current trajectory shows AI will continue to be this profoundly powerful, transformative force. It's reshaping industries, science, culture, our daily lives in ways we're really only just starting to grasp. The journey is far, far from over.
Which brings us perfectly to our final thought for you, our listener, as we close out this deep dive. Given AI's really clear cyclical nature, its amazing resilience through all those booms and busts, and its undeniable profound impact right now, what new summers and maybe even winters might lie ahead on this journey? And maybe more personally, how will you navigate this? How will you adapt to and perhaps even help shape a world that's becoming increasingly intricately interwoven with these intelligent systems? This journey of discovery, of understanding, and figuring out how we live with AI, it really is just beginning for all of us.